Okay, today we're going to be looking at differential equations. Solving differential equations is a skill that you will hone and develop over all your years of calculus and even into hopefully a course called differential equations. Differential equations can come in many different varieties that require different techniques. The particular one that you should be able to solve as a first-year calculus student is called a separable differential equation. Let's take a look at this question that I just kind of made up. Okay, the total tons of plastic in a body of water suffering from human pollution is estimated to be changing with respect to T years since 2000 at a rate of 10 plus 0.4 P, where P is the current tons of plastic. What this situation is telling us is that however much plastic is in this ocean, this body of water, the amount that's going to increase over that year is related to how much there is in it. And you can see from this equation, this expression here, the sad part of this story is that the more plastic is put in, the more it will increase the next year. So let's take a look at our first question. If there are 100 tons of plastic in the ocean in year 2010, use a tangent line approximation to estimate the number of tons of plastic in year 2011. Using tangent line approximations in differential equations is so important. There are so many different differential equations that are known in science and math and all sorts of applications where we don't know the particular solution to it, but we can still use that differential equation to help make estimates because of this skill right here. So it's really important that we understand this. Okay, we know that a tangent line approximation is of the form y minus y1 equals slope times x minus x1. So that tells me, given a point on a curve, I'll make the point right here actually. Given that point on a curve, the tangent line, would look something like that. Oh, we can do better than that. We can make a line here. Something like that. And we can use that tangent line to estimate values around that point. All right, well, we've actually been given quite a bit of information here in this problem. First of all, let me rewrite this equation in terms of P's and T's, since we know that our Y value is the plastic P, and our X value is the time T. So I'm going to call that T and T1, P and P1. Okay, so at this particular moment, we know there's 100 tons of plastic, and the T value is, since it's years from 2000, it is 10. Okay, so let's make this P. Remember, P is going to be a variable in our line. We need that. Minus 100. That's the amount of tons of plastic at this moment. We don't know M yet. We'll come back and get that. And then this is T minus the year was 10. Okay, now we need to estimate this slope of the tangent line using, well, we can get the exact value actually using that equation there. That equation says that the rate of change in P with respect to T is equal to 10 plus 0.4 P. So when P is 100, I can simply plug that in for P. Oh, I got one too many zeros there. Let me get rid of one of those zeros. There we go. Okay, now this one's pretty easy to evaluate, but I want to remind you that there's absolutely no reason for you to evaluate this on the AP exam. Just put that value in parentheses right there. Okay, but since this one's so easy to evaluate, I am going to go ahead and do that and put in 0.4 times 100 is 40, plus 10, that's 50. Okay, so the rate of change is 50 there. So I'm going to just move this 100 over to the other side, and then I get t minus 10 plus 100. Now I can use this to estimate the value of p in the year 2011. In the year 2011, the t value is 11, which makes this 11 minus 10 is 5, is 1. So this is 50 times 1 plus 100. And again, there's absolutely no reason to evaluate this on the AP exam. You just have to plug in the numbers and then you can be done. This one's so easy though, I'll just go ahead and say that it is 150 tons. And we are done with that one. All right, let's take a look at the next equation. Next question. Represent the relationship in this problem as a differential equation. Well, we actually already did that over here, so we'll do that again. So we were told that the rate of change with respect to time in years is equal to 10 plus 0.4 t. Oh, no, 0.4 p, excuse me. All right, well, we need to find a particular solution. So they're asking us to solve this. This is a differential equation that you can solve. This is not something that it requires more years of calculus than what you've done. So that means it must somehow be separable. You know, I've seen separable equations that are kind of tricky. You got to factor them first. You got to do a lot of manipulating. And I've seen others that are very, very obvious. This one here is, you know, kind of a little bit tricky, I guess. But it's not the worst I've seen, of course. What I'm going to do is just put parentheses here, and I'll multiply both sides by dt. So I'm separating the dp and the dt. That's super important. But the goal when doing separation of variables is we want to get all our p's with our dp's, all our t's with our dt's. And let's see, what does that give us? Well, those go away, right? So I'm left with dp is equal to 10 plus 0.4 p dt. Okay, now at this point, I need to get the p's to the other side. And in order for this to be solvable as a separable differential equation, I don't want plus signs making separate terms. So I've got these, you know, two terms here that I started with, the 10 and the 0.4 p. But when I put the times dt to that, I end up getting really just one big term here, and I can divide this now by 10 plus 0.4 p. So we don't end up separating out the 10 and the 0.4 p. They're gonna be tied together, which is perfectly fine. Okay, so that finally gets our variable separated as dp over 10 plus 0.4 p is equal to, well, on this other side, all I've got is just dt. And that's fine. I need either t's to be over there with a dt or just a dt or just a number. But these are now separated, so we can integrate. So the right-hand side of this integral is, well, that's pretty simple, isn't it? The integral dt, well, that's just t plus a constant c. So I will say that, t plus a constant. Technically, we'd get a constant on both sides of this integral, but I'll just put the constant on one of the sides, and I like to do it on the independent variable t. All right, this is basically very similar to u prime over u. So if I have the natural log of some function u, then its derivative is equal to u prime over u, or du dx over u. This is really close to exactly what we need, but we need to do a substitution. So I'm going to let u equal 10 plus 0.4 p. Then I'm going to take the differential of each side, which gives me du equals 0.4, the derivative of the differential of 10 is 0, 0.4 p gives me 0.4 dp. So this ends up being, now 0.4 is 4/10, which is 2/5. So I'm going to multiply both sides by 5 over 2. So this is 5 over 2 du. And I just felt like that's a little bit easier than dealing with du divided by 0.4. But you know, you could do it either way. So let me just make that note. 0.4, that's 4/10. And I can reduce 4/10 by dividing the top and bottom by 2. That makes it 2/5. Then multiply both sides by 2/5, and I've solved for dp. All right. So that makes this integral, when we do a u substitution, the dp became 5/2 du. And that 5/2, well, that's just a constant. We could pull that out in front of the integral. And then this is du. And then the 10 plus 0.4p, remember that was just u. Okay? Now when we integrate that, we know the integral of du over u. That is the natural log of the absolute value of u. So this becomes 5/2 times the natural log of the absolute value of u. And what was u? Well, that was 10 plus 0.4p. So we'll go ahead and put that back. 10 plus 0.4p. And that is equal to t plus c. All right. The nice thing that we want to try and do is get rid of the absolute value bars. And we're hoping that we can do that by doing something I call playing fast and loose with our constants. First thing I'm going to do is get rid of this 5/2 by multiplying both sides by 2/5. So let's multiply both sides by that. You know what, I should probably use a different color so that you know that it's a second step, but I just don't want to rewrite all that. So this is my next step in my work, multiplying both sides by 2/5. Okay, now what does that give us? Well, it's going to give us the natural log of the absolute value of 10 plus 0.4p. And then over here, we're going to get 2/5 times t. Well, that's 2/5 t. Now, c times 2/5 is, well, a different constant, but I can still just call it c. It's not the same value that this c was, but still just an unknown constant. I'll just call it c. All right, now to get rid of the natural log, I'm going to exponentiate both sides. So that's gone. And I've got these absolute value bars, but I'm not going to need them anymore. And I'll explain why in just a second. So this becomes e to the 2/5 t plus c. All of this is an exponent, but we know that when properties of exponents say that, if I've got e to the a times e to the b, that is equal to e to the a plus b. So what that tells me is that I don't have to write it with the c up in the air like that. I can realize that this is e to the 2/5 t times e to the c. But what is e to the c? Well, it's some constant. So this is e to the 2/5 t times another constant, which I'll pull it out in front. Okay? Now I'm simply just going to solve this for p. So this is 0.4 p equals c e to the 2/5 t minus 10. And remember we said that that 0.4 was actually, it was actually 2/5. So I'm going to go ahead and write it like that again. And I will now cancel that by multiplying by 5/2 on each side. Okay, finally we have got the general solution. So this is p equals c e to the 2/5 t times 5/2. Well, c times 5/2, well, that's just a c. So again, we're left with c e to the 2/5 t. 10 times 5/2, divide 10 by 2, you get 5, and 5 times 5 is 25. So this is minus 25. Okay, now let's go back to the question. Let's scroll up and let's find that. And we were told that there were 28 tons of plastic in the body of water in 2000. So we should be able to plug that in and do that. They've given us a nice, easy one to plug in. The year 2000 means that t is 0. So p of 0 was 28 is what they told us. So if you put a 0 in right here for t, this whole thing becomes e to the 0. And e to any exponent, any base to the exponent of 0 is 1. So e to the 0 is 1. So that's telling me that when t is 0, we have simply c minus 25, and we were told that that equals 28. Let's see, I think I can make this into a 28. There we go. So I think you can see that if I must have had a c value of 53. And that's our value. So our final solution to this particular, I'll just write it over here, p as a function of t for this particular situation is 53 e to the 2/5 t minus 25. That's the final answer. Okay, that's the meat, the big part of this problem. I did want to add one little fun excursion so we can look at a differential equation that you couldn't solve in calculus, but we could practice verifying it. Okay, let's look at this one. It is found that for t greater than or equal to 1, the rate at which plastic can be removed from the water using a special new technology can be represented by, can be represented by the following differential equation. T, the time in years, remember we're stating that t is, this is t greater than or equal to 1. So I guess we had to wait till 2001 for this to be invented. With the number of years times dc dt, that's the rate at which it is cleaned up, plus the total amount cleaned up equals t squared minus t. I just kind of made up this equation that is solvable with some techniques that you learn your first few weeks in a differential equations class. Whether or not this would actually be something that would happen in the real world, I don't know. Well, maybe, anything's possible. But here's the key. You cannot solve this. Okay? So no by Cal 1. Okay? Those of you that are in differential equations, if you happen to be watching this video, feel free to solve this one by the usual techniques. But what we have been given is a solution. This is a solution. There's many solutions to this differential equation. But we're given the initial condition that C of 1 equals 5/6. So what that means is that this equation not only satisfies, so this solution satisfies that rule, but it also has to satisfy that rule. And we've been asked to verify it. And if this was an equation that you could solve, you could verify that solution by going through all the steps like we did in part B. But if they ask you to verify something, it's typically easier to just verify that it follows both rules. I picked this equation because I wanted to force your hand to doing it by verifying. Well, let's take a look at a little closer what this equation says. It says t times dc dt. So we need to know what dc dt is. Well, there's c as a function of t. So dc dt, or c prime is dc dt here. There's another way of saying that. So c prime of t, we can find that pretty easily, can't we? 1 over t, the derivative of 1 over t would be a negative 1 over t squared, right? Because you would make that t to the negative 1, and then the derivative gives you negative 1 t to the negative 2. All right, I've got plus, I'm going to bring the exponent down on the t, so I have 2t to the first over 3. The over 3 just comes along for the ride. You don't need to worry about it. No quotient rule or anything silly like that. All right, minus t over 2, that's, well, the derivative of t is 1. And so again, the over 2 is a constant. It just comes along for the ride. Okay, so that is what goes right here. So let's write out what we have. We have t, right? And then that dc dt, we agree, is another way of writing that is t prime. So I'll do that. Okay. All right. And I'm just putting in what they say. Okay. And I think I'll write my t to the side of that fraction. I have the right to do that. Okay. And then minus 1/2. Okay. All right. And then I have plus c. Well, I'm hoping all this stuff will simplify down to t squared minus t. So I don't want c's in it, but I have an equation for c. So I'm going to add my equation for c, which was 1 over t plus t squared over 3 minus t over 2. All right, pardon me, just a second. Get my bearings here. Okay, and then that is magically supposed to equal t squared minus t. Well, let's do some algebra and hope for the best, right? Go there, there, and there. Okay, so it's going to give me negative 1, and t over t squared just becomes a negative 1 over t. All right, this becomes plus 2/3 t squared minus 1/2 t. Then we got plus 1 over t plus t squared over 3 minus t over 2. Okay, well, hopefully we can chop some things off here. All right, well, that one's got a partner. All right, this is negative 1/2 t minus t over 2. That's the same as negative 1/2 t. So I think you'll agree that we do have a total of a minus 1t. 1/2 minus 1/2 is minus 1. And I've got 2/3 t squared plus t squared over 3. 2/3 plus a 1/3 is a whole. So that's t squared minus t. And we verified the first part. All right, the only other thing to verify is that c of 1 equals 5/6. Well, let's c of 1. That just means we put in 1 for t. And I get 1 over 1 plus 1 over 3 minus 1 over 2. So if I make these all in terms of 6, I get 6 over 6 plus 2, multiply the top and bottom by 2, 2 over 6, and then I'll multiply the top and bottom by 3, minus 3 over 6. We get 8 minus 3 is 5 over 6. So that is just what we wanted. So that's how you can verify a solution without having to actually find it by solving the differential equation. All you have to do is check that the equation holds here, and then it holds here.